We'll start our treatment of the thermodynamics of chemical reactions on what I hope will be very familiar ground for you in talking about heats of reactions. This is often material that we cover in general chemistry, so a lot of what I'll say in this video should be familiar and hopefully will be something that you can easily renew your memory of and your usefulness of. All right, now in a chemical reaction, we're going to assume that we're doing a reaction under conditions of constant pressure. So that means that any heat that's generated by the reaction or any heat that's absorbed by the reaction is basically equal to the enthalpy change. And that's one of the reasons why we tend to measure enthalpy preferentially and not internal energy. Now, one of the things I'll note about this is that for the reaction, the internal heat exchange or heat interaction, and maybe I'll write it like this, is always equal to the negative heat interaction under constant pressure of the surroundings. And it's often these that we actually measure when we're trying to determine an enthalpy change for a reaction, because if we have surroundings that are well characterized, we, for example, might know their constant pressure heat capacity and simply measure a temperature difference. And so by using calorimetry, this is a way that we can get a handle on the enthalpy change for a reaction or enthalpy change for some other process. All right, so this is a very common way that we use this, and I even have labs that are involved in making that measurement. Now, just to keep things simple, I want to write a very simplified form of a reaction, which is just basically A going to B. Now, even though this looks like it's one molecule going to another, I want to encourage you to think very liberally about A and B. In other words, A could represent a set of reactants, and B could represent a set of products. Okay, I don't want to get tied down in rewriting over and over again some long list of reactants and products. Okay, but A goes to B just represents a general reaction going from reactants to products. Now, what I want to do is review three particular properties of enthalpy that we know are true of enthalpy in general, and talk about how they help us in getting to the bottom of the enthalpy change for a reaction or a set of reactions. All right, first of all, I'll note that enthalpy is a state function. And the fact that it's a state function means that there are certain qualities and certain properties it's going to have that will be of use to us. Okay, the first of these I'll indicate is basically reverse processes. In other words, if I were to run this reaction as I've drawn it in reverse, that is going from this side to this side, there's a very predictable outcome that it will have for the enthalpy change. So in other words, if I have A going to B, and this involves an enthalpy change that I can write, for example, as the amount of heat at constant pressure for AB. Okay, so simple notation. All right, then what I would claim is if I look at the reverse process, B going to A, the enthalpy change will simply be the negative of this heat change. All right, straightforward enough. All right, how do I know this? Well, let's suppose that I have a diagram like this where enthalpy is my vertical coordinate, and the stuff down here is A and the stuff here is B. Could have been the other way around, doesn't really matter. All I know is that when I go in the forward direction, I'm starting with A as my initial state and going to B as my final state. And in this particular case, I would write that the change in the enthalpy would be QAB, where QAB is just this. It's basically the enthalpy of B minus the enthalpy of A. All right. If I were to do the reverse reaction, this reaction, then I would be starting with B and going down to A. And I think it's easy to see that because H is a state reaction, it depends only on the initial and final states. So in the first case, the initial state was A and the final state was B. In the second instance, the initial state is B and the final state is A. So the distance in enthalpy between those two is the same, but I'm going in the reverse direction. So now in this case, I'm going to get a negative sign because I have reversed the direction of my change. I've basically reversed the roles of the initial and final states. Okay, so fairly easy. A second property, and this again arises from the fact that delta H is a state function, has to do with additivity. In other words, if I have a reaction, let me switch to purple here. If I have a reaction, A goes to B, and I have a second reaction, so I'll say followed by B goes to C, then if delta H of this first process is QAB and delta H of the second process is QBC, then the total process, so I should probably make it a little arrow here, is going to be the sum of these two. All right, so how would I think of that in terms of drawing a picture? Okay, so again, I'll make this a really simplistic picture, although I could have ordered these energy levels any way I want. This will be A, this will be B, and this will be C. So if I'm going from A to B, then B to C, okay, with corresponding heat changes AB, QAB, and QBC, then I think it's pretty obvious that the total heat change for this process is just going to be the sum of those two. Now, I've written this so that they're both positive quantities. I could have written it in such a way that one of these was a negative quantity. They still add up, but you have to pay attention to the sign of the heat change in order to track that change as we're going through this. All right, the third property that I would mention is something I'll call extensivity. Okay, and we've noted that, for example, if I have a molar heat change and I subject that molar heat change to n moles that are undergoing that heat change, that would give me a total heat change for the n moles. Okay, so this extensivity property of enthalpy also works in reactions. So in other words, if I have, again, my signature reaction, A goes to B with a delta H of QAB, then if I double the amounts, and so I could write this symbolically as 2A goes to 2B, then the delta H for this process is going to be twice as great. And I think this intuitively makes sense for us. If we're using twice the amount of material, it's going to double the amount of heat change that occurs in the chemical reaction. I don't have a good diagram to write this sensibly, but I'll draw something that might drive this home. If I have basically one sample of A that goes to B and a second sample of A that also goes to B, and I run these separately, I'll generate QAB from this reaction, and I'll generate another QAB from this reaction. So the total heat that I've generated from running each of these would be the sum of the two. Basically add them together. Okay, I think we also know that if there is a series of reactions, I mean really where we're leading this to is if I have a series of reactions and I go, for example, this is H along the vertical axis, and I go, along this series of reactions, something like this. So I've gone from A to B to C to D to E, and my enthalpy changes for each of these processes are delta H1, delta H, then delta H3, and delta H4. So the delta H for the entire process would simply be the sum of these different components. All right, what we've done here is basically given you the outlines of what constitutes Hess's law. All right, and Hess's law is something that hopefully you've seen before in general chemistry, but it basically means that when you add chemical equations together, you add their enthalpies to get the net enthalpy change for the resulting reaction that is the sum of the two reactions.